Today in Campechi's Corner, we're going to look at simplifying radicals, and this is day 2. When the directions ask you to put a radical expression into simplest form, there's a couple things you need to look at. First of all, we want to make sure that we don't have any perfect square factors other than 1 in the radicand. We've simplified all the perfect squares out of that. For example, in the square root of 8, I have a perfect square of 4, so I need to simplify that. Square root of 4 times the square root of 2 gives me 8. So when I simplify, the square root of 4 is 2, so my final answer there is 2 root 2. The other thing is we don't want fractions in our radicand. So for instance, if I have the square root of 5 over 16, I want to split that into 2 radicals. And square root of 5 can't be simplified, so that's going to stay as is. But the square root of 16 is simplified to 4. So my final answer there is going to be the square root of 5 over 4. Our last form of simplification today, which is going to be new to us, is we don't want any radicals in the denominator of a fraction. So for instance, if I start with 1 over the square root of 7, today we're going to learn how to rationalize the denominator. I'm going to multiply top and bottom by the square root of 7. And the reason I can do that is because root 7 over root 7 simplifies to 1, so I'm not changing the value of our original fraction. That will simplify to the square root of 7 over 7. Now to get us ready to rationalize the denominator, let's look at a few things. We have up here that says to eliminate a radical from the denominator, you multiply a radical expression by an appropriate value of 1, and we'll talk about that in the next few problems. When we're multiplying it by 1, we're not changing the value of the original problem. This process is called rationalizing the denominator. Now, rationalizing the denominator is a common term used in many math classes, so this really is an important concept. So as we're getting ready to do it, do you see the pattern? Look what happens. I have the square root of 7 times the square root of 7. Now I can multiply what's underneath, so that gives me the square root of 49. 7 times 7 is 49. What is the square root of 49? 49 is a perfect square. That answer is 7. Let's look at the next one. Square root of 5 times the square root of 5 gives me the square root of 25, which is 5. Now again, are you starting to see the pattern? Anytime I multiply a radical by itself, in the end, I'm just going to get that number without a radical sign. Let's look at the third example there. Square root of 11 times the square root of 11, again, gives me the square root of 121. But I'm noticing my pattern. I can just skip that step. The square root of 11 times the square root of 11, because the radicands are both the same, I can just say my final answer is 11. Looking at our last example here, that number is pretty large. The square root of 126 times the square root of 126. I don't even have to use my calculator to multiply that and then figure out what the square root is. I know my final answer is going to be 126. So now we're ready to practice some, so let's simplify. Now in number 1, remember we always want to split our radicals. So I have the square root of 1 over the square root of 13. The square root of 1 is a perfect square, it's 1. Now the square root of 13 is not a perfect square, and there's not a perfect square that goes into 13. Now this is where I need to rationalize the denominator, because the rule is I can't have a radical sign in my denominator. So I'm going to multiply top and bottom by the square root of 13, because when I do that, because it's the same thing, I'm really multiplying that fraction by 1, so I'm not changing the overall value. 1 times the square root of 13 is going to give me 13. And in the exercises we just did, root 13 times root 13, I know is 13. So that's my final answer right there. And number 2, same idea. Square root of 4 over the square root of 7. Now the square root of 4 is 2 over the square root of 7. Now again, the square root of 7 is not a perfect square. There's not a perfect square that goes into 7. So I'm going to rationalize the denominator, multiply top and bottom by the square root of 7. And I have 2 root 7 over 7. Now I can't simplify what's inside the radical, so this root 7 stays as is. I can't simplify this 7 and 7. If it were possible for me to simplify what's on the outside, that 2 and 7, I would do that, but in this case it's not. So my final answer is 2 root 7 over 7. In number 3, the same thing, so I'm going to split that the square root of 1 over the square root of 18. The square root of 1 is 1 over the square root of 18. I'm going to multiply top and bottom by the square root of 18. So I have square root of 18 over 18. Now the square root of 18, there's a perfect square that goes into it. It's 9. So I'm going to do the square root of 9 times the square root of 2 over 18. So that gives me 3 root 2 over 18. Now again, like we talked about in the last problem, this 2 and 18 I can't simplify, but I can simplify what's on the outside there. So I can say that 3 goes into 3 once, so that can become 1, and 3 goes into 18 6 times. So my final answer there is going to be root 2 over 6. Let's take a look at a few more problems. In number 4, the square root of 27 over 15. Now I notice both of these are divisible by 3, so let's simplify that first. 27 divided by 3 gives me 9. 15 divided by 3 gives me 5. So I get the square root of 9 over the square root of 5. The square root of 9 is 3 over the square root of 5. 5 can't be simplified. So again, here comes my step where I'm not rationalizing the denominator. So I have the square root of 5 over 5. So my final answer there is 3 root 5 over 5. In number 5, I have 15 over root 5. Now I don't have to do anything to the top. That 15 just stays as is. Again, root 5, I need to rationalize, so I'm going to multiply top and bottom by the square root of 5. And I get 15 root 5 over 5. Now again, I notice on the outside I can simplify. They're both divisible by 5. 5 goes into 15 3 times and into 5 once. So my final answer for this one is going to be 3 root 5. In our last problem for today, 60 divided by 5, the square root of 60 divided by 5, and we have a negative 1 in front. Again, 60 divided by 5, that actually goes evenly. 60 divided by 5 gives me 12. So I'm going to make that negative sign there. This just becomes a 12, a square root of 12, no denominator. So I'm just going to simplify that. My highest perfect square that goes into 12 is 4. So I have the square root of 4 times the square root of 3. So the square root of 4 is 2. So I have negative 2 root 3 is my final answer.